Good morning. Okay, so let's start the lecture, and we're going to start a new topic. So after lecture 16, when we are finished with first order differential equation, so the logic step is going to be a second order differential equation. But we need to solve the complex number in order to solve second order differential equation. Okay? So we need to cover this concept complex number first, and then we'll go on to the second order differential equation. Okay? What lecture is this about? Lecture 14, I think. So the cutoff material is done up to the bigger than that first order differential Okay, first of all, definition of complex number. Yeah, I noticed the video records sometimes the sound is good, sometimes not. Probably when I was talking to the computer is good, and talking to the video, the sound kind of turns off, right? We're going to use, very generally people use a Z to represent a complex number. So more calculation. So, definition of complex number is Z plus Z equal to A plus I B. Okay. So this is a complex number. So basically, we need to understand complex number is not the same as a real number. And why is that? And first of all, let's say what A and B are A and B. They are real numbers. They're real numbers. So what is this I and C? That's the difference. I'll tell you what this I and B is, but first of all, complex number must have two parts. This is kind of real parts of the imaginary part. So this A and here, this is parts. This part is called the real part. This is that. This is the real part. And B and here is called the imaginary. So this I and this is imaginary. Like the name says, it's imaginary. It's not real, right? It's something people thought from inside their head. Right? But you don't see this complex number in the real world, but it's very useful in mathematics and many other applications. So that's A and B. This I or G, this is so-called imaginary units. Imaginary unit. So you can see if you have a complex number, you can see the G or I. Mathematics experience, you can see mathematics, you can just type A plus G. You don't need to type whatever it is. Just type G and then another real number, and it gives you a complex number. So this I or G, I'll just write I here. Okay, mathematically it equals the square root negative 1. That's what this imaginary unit is. So this is actually where this kind of a untraditional kind of things come into picture, because in old time, when people looking at the mathematics, square root, anything under square root has to be greater than 0, right? Yeah. So, but then sometimes this guy, I don't know which guy, but come up with the idea, how about square root of -1, right? Or how about square root of a negative number? Then what do we do? So they come up with this idea of the square root of -1 equal to I. That's basically where it comes from, right? Even at the beginning, it seems to be very realistic, because people think, well, what's the meaning of this, right? Why would you define this one here? Why would it be there would be a square root of a negative number? Right? It doesn't make any sense. But the proof that it makes a lot of sense in some of situations. So that's basically what happened. Now, if I use a graphical approach to show the complex number, just like you show a coordinates in a Cartesian coordinate. So you still draw some complex plane. So this is called a complex plane. Okay. Yeah. And we also have two axes. And this is called the real axis. This is called the imaginary axis. So instead of calling x and y axis, right? Real axis, imaginary axis. So when we have a complex number, say a plus 2e, so a is the real part, right? So a, where's a? Maybe a is here, right? And where's b? B is the imaginary part. Location of a is complex number. This location is the z complex number. Okay? So that's how you use complex plane, okay, to show where this complex number is. The same way as you do regarding Cartesian coordinate, just change the x and y to real and imaginary, right? So sometimes this is also called the Argand, okay? This is also called Argand diagram. Okay, it is a very good website. It's really advanced, and take a look at this website, www. .org. So dimensions/math.org. So this website has many videos in it, and those videos are very good animated videos using different softwares, and they talk different topics in mathematics. One of the topics is on complex numbers. Okay? So you can take a look at it. They call it chapter 5 and 6. So those chapters are on complex numbers. Very, very interesting video. Okay, so that's complex number basically. Okay. Yeah. Now let's take a look at operations on complex numbers. Basically, for real number you can multiply and divide, right? So we're going to have similar things. What do we do with complex number, and how do we manipulate complex number? Okay, operations. So therefore, I will show this very simple. When I write, sometimes I write I, sometimes I write a J. So just know that they all refer to a complex number. Okay. So let's have two complex numbers here. And now I'm going to add them or subtract them. So the basic rule is when you do addition or subtraction, when you do addition subtraction, all you need to do is just add or subtract this real and imaginary part correspondingly. Okay? Yeah. So here's B1 plus minus A2, and then plus J, B1 plus minus B2, like this. right? So that's the Bayesian subtraction. So you're essentially separating the real and imaginary part. Okay, so then basically, there is one observation on conjugates. There's one operation that's dedicated to complex numbers called conjugate of a complex number. Z. Conjugate complex number Z. So, the notation-wise, some consequence of basically we use Z bar to represent this conjugate of this complex number. Conjugate, it's a word in basically, it's taking not the negative of that, but it's almost like taking the opposite of this thing here. Okay? So this conjugate, if Z is A plus JB, then the conjugate is A minus JB. So the real part's not changing. The imaginary part changes into negative. Okay? That's conjugate. So sometimes the notation is also Z. There's a bar, Z bar in the head. So that's another way of writing a conjugate. Okay. Okay. So those are the operations, simple versions. We'll talk about the multiplications later. Okay. And let's finish the conjugate first, and then I'll ask you a question. So what does it look like on a complex plane? For between this original complex number and this conjugate of this complex number. Okay. Original one is here. This is original one here. Okay. The original. So I'm gonna connect this origin to that point. Use a segment line here. Okay. So that's basically the original complex. Actually. You have a point here, origin to that point. It's like a vector, right? It's like a vector. As a matter of fact, a lot of times, if you think of this complex as a vector on a complex plane, you actually can easily explain some things there. Yeah, even though you cannot say that is the vector, right? Okay, so this is your original one. The real part's not changing, but the imaginary part becomes negative b, right? Become negative b. So the conjugate of that number basically end up over here. And this is essentially, it's the mirror of that original one here. So this is a Z star here, right? The mirror of that. Okay, good. One of the simple facts here is when I have the Z and the original Z over here, okay, and the original Z, and see what happens when you add them together, right? See what happens when you add them together, and then what happens when you subtract things, subtract from each other. That plus that star. So what does that give us? Plus this together, see what happens, right? So A plus A and GB plus GB squared cancel each other, right? So you have 2A over here. Okay, you have 2A. So in other words, you can see now, I can see my A, right? The A, which is basically this number here, right? And what's A here? A is what we call the real part of this complex number, right? So A is basically the real part of the complex number. And that equals to Z plus Z star divided by 2. Okay. So that's the one little fact that we find out here. Now this fact seems to be maybe not quite useful because you say, well, if you want to find an A, you need a Z and Z star, right? And A is part of Z and Z star. So what's the point of you relate all of this one together? It's a little useful in sometimes in terms of proving something. And sometimes when you want to transform the operation, and instead of just using this real part, the A at here, you use the original Z and Z star. It actually can simplify the computation somehow. Okay? Yeah, so just remember the fact. A can be extracted out of the addition of the Z and its conjugate divided by 2. Okay? Yeah. So, similarly, if you then subtract Z star, so that subtract this, so it's 2AB, then the B, which is the imaginary part of Z, and that equals to Z minus Z star divided by 2J. So at this stage, I want you to think of those I or J as one number here, okay? It's a complex unit, square root of -1. So when you divide this guy here, it's just like regularly dividing a number, but this is going to be complex, basically, imaginary unit. Okay, so let me ask you a simple question here. Is Z equal to 3 a complex number? Why not? Okay. So it doesn't have imaginary parts, right? So what's the imaginary? It's supposed to be here, but what is B equal to 0? B cannot be 0? I didn't say B cannot be 0. Right? I just said Z equals A plus 2B is a complex number. And A and B are real numbers, so which means A and B, both of them can be zeros, right? Can also be zeros. So which means, is this Z equal to 3 a complex number? It is. Right? So, this is something I noticed in the past, a little confusing. This is still a complex number. Okay? It's still a complex number. Okay? Except that this imaginary part of Z equal to 0. Okay? So, actually, a better way to explain the relationship between this complex number and the real number is just look at this complex plane. So we look at the complex, remember when we said this axis here is called what? The real part, right? A real part is basically the numbers on it is real numbers. So all the real numbers is here, right? All the real numbers is here. So when you have an imaginary number equal to 0, all the real numbers is here. That make sense? So complex number is essentially it's a bigger sort of a level of the box here, right? Complex number contains all the real numbers. When you let the imaginary number equal to 0, it becomes a real number. Okay. So that's what we can see here, right? So complex number is kind of bigger box. So that's, you should remember that. So then turn into real when imaginary equal to 0. Yeah, a lot of times so when I later when you see in some situation I will give you a question saying what's the we haven't learned this, but what's the nth root of the complex number 3? Right, so you shouldn't be questionable. Well, 3 is not a complex number, but we're just in general saying that's complex number. Okay, so addition, subtraction, conjugate, okay, and then multiplication. Okay, multiplication. Okay, so let's look at the multiplication and how we carry it out. So we're going to do this Z1 equals A1 plus 2B1, Z2 equals A2 plus 2B2. Okay, to carry out the multiplication. So now we can carry Z multiplied by Z, which is this complex number multiplied by this complex number. Now remember I said when you do manipulations, you treat this J or I, whatever you write there, you treat it as a number, okay, as a quantity. Okay, treat it as a quantity. So when you do multiplication, so we're going to treat it as quantity here. So A1, I do this expansion of this multiplication. So A1, A2, A1, A2, and then A1 multiplied by this guy here, and then this guy by this A2, and here J by J is J squared, and B1, B2. So this is a regular expansion of multiplication of two brackets here, right? Two brackets. Yeah. So you're basically treating G as a regular quantity here. There's nothing different from the A and the B, right? A and B here. Okay. So this middle terms here, that can be simplified into this A1, sorry, what was this? A1, B2, B1, A, this is B1, right? This is B1 here. Okay. So then G squared, B1, B2. Okay. Yes, yeah. Just minus this. So I'm going to talk about this here. So the point here is, what is G squared, right? What is G squared here? Well, I guess you already know that it's G squared. So basically, G squared is G multiplied by G, right? G multiplied by G. And what is G? G is defined as -1. G is defined as -1. So then, you get G squared. Square roots multiplied by itself, you end up with, right, what's under the square root, right? So -1. So you can replace this with -1 and then this original one is A1, A2 minus B1, B2 plus 3 A1, B2 plus A2, B1. So sometimes the complex number operation is not as simple as not as easy as let's say it's still simple, but it's just not as easy as two real numbers multiply each other, right? If you have an engineering calculator or a MATLAB, it's quite simple, just function and do a regular multiplication. Okay, so now the little question here is, interesting is, this G thing here, okay, this G. So this G, okay? So I'm going to use a little graphic thing here to have a better understanding or appreciation of this G over here. So this is a complex form. Okay, this is complex form. So let's say I'm going to do this. So I'm going to start with a 1. So starting with 1, this is 1 over here. So starting with 1, then the next step is I'll use 1 multiplied by G. So now I'm multiplying the G with the original 1. Right? So if I just simply look at this, 1 by G is G, right? So if I look at from complex form, so where is the G here? So you're after this multiplication, you went from this 1 to 0. So basically, how much do we take in? 93, right? Yeah. Okay, so now we do this. So this is G now, right? This is G. So then we multiply the G with the previous results again. Okay, with the previous results again. So you know that this is -1, right? You know this is -1. Okay. So then, when I look at the complex form here, there we go. Because this is -1 coming here, right? Here. So basically, goes over here. So graphically looking at this point here, this is 90-degree rotation here. So it's another 90-degree rotation, counterclockwise rotation. So when you keep going, right, you can imagine now, if this is g squared, right, this is g squared. If you multiply another one, it's going to be g cubed. Okay. Right? Yeah. I guess you cannot give me an answer immediately. What would be this one here? Negative g, right? Negative g. So here's another rotation. Negative g. Right? So finally, g4, you end up with this back to number 1. Right? So this actually tells us an interesting fact about this g at here. Okay, this g. So this g is it's like a rotating operator. So when you multiply the g with anything, so that thing will rotate how much? 90 degrees. Right? So in energy processing, if you have a little indicator here and you want it to rotate 90 degrees, so what do you do? Multiply by g. Okay? So that will be like this. Okay? That's the rotation, actually. In robotics, we have similar things here. But we realize that using the rotation matrix, right? Yeah. As a matter of fact, it's the same thing, actually. Yeah, a lot of things behind the mathematics, they all end up with the same concept. Yeah. They actually have the same kind of root. Okay. Yeah. So just think of a J as a 90-degree rotating factor here. Okay. Yeah. Okay, so that's multiplication. That's multiplication here. So now let's take a look at the one simple example. I have z equal to this. Calculate this z multiplied by z star. So z is the complex number. Z star is the conjugate, right? You just learned conjugate. By z star. Conjugate, which is star x3, right? Okay, what does this equal to? Do a regular calculation. A by a squared. A by that, negative. A positive. This by this, negative g squared, b squared. Is that right? Yeah. So this cancel this, right? This cancel this. B squared is negative 1. So negative, negative, positive. So overall, okay, a squared plus b squared. A squared plus b squared. So what is a squared plus b squared? Right. So what's a squared plus b squared? What's the distance from here to here? Yeah. So let's see here. Now I'm going to use this number here, this symbol here, okay, absolute value of a z. Okay. So it's just like absolute value of a vector. Okay. Absolute value of z. Representing the distance from here to here. So if I think of this vector, or just a simple quantity here, the difference is just the square root, a squared plus b squared, right? So now you can see the calculation what it just showed us is z multiplied by z conjugate give us the power of this distance. Right? So that means the absolute value z is basically square root z star. Okay? Z multiplied by the conjugate. Okay, good. That's multiplication. Numbers. Now let's look at division. Division is probably the most difficult kind of operation involving complex numbers. So talking about Z1 divided by Z2. Oh, by the way, let's see, if Z is equal to just a real number, what is conjugate? 6? 3. Still 3 here, okay? Okay, so when you do division operations here, what you do is, okay, basically the idea is, here on the denominator you have a complex number, right? But we don't like the complex number on the denominator. Basically, that makes sense, it's complicated. So then the whole point is we want to get rid of the complex number on the denominator. And that's the whole point when we do division. So how do we get rid of this complex number on the denominator? Well, if this is a complex number, look at what happens to it here, right? What if I turn a complex number into a real number? So what do? We can multiply this with the conjugate. So that's how we can turn it. So basically, I don't want it to be a complex number. So I multiply this with its conjugate. Then it'll become a real number. However, you cannot change this original one here, right? You cannot change this here. So the multiply is at a denominator location, and you have to multiply it on the numerator too. So that's basically keeping it as simple. But this way, you turn this denominator become into a real number, and this top one here, I don't know what it is, but it's going to be just a simple multiplication of two complex numbers. So all you need to do is just carry out a multiplication on the top and divide at the bottom. So that's basically Z2 squared here. That's it. That's the whole idea of this division right here. That's the whole idea of division. Yeah, this complex number computation, you need that in many other courses. In the next year, 254, in control system, in signal processing, in electrical engineering. So this thing here, okay, is the fundamental operations here. So you need to be very, very proficient in terms of operations, okay? Not just calculation using calculators or math labs, by hand. You know, this is some of the things by hand. Let's take a look at one example. So this complex number divided by this complex number. Okay. So let's try the approach that we just showed it here, and how do we simplify that? Okay, so as we said, we're going to just basically turn the denominator into a real number by multiplying its conjugate. 5 minus j2. So that's how we turn into a real number. Right? We need to multiply this 5 minus j2 on the top. So I'll give you 15 seconds here, see if you can answer the answer here, the computation skill. 15 seconds up, and supposed to get an answer. So, oops. Yeah, how many of you got it? Yeah, okay, not many. That's okay. So, we're still learning, right? So let's do it together. The bottom here, 5 squared plus 2 squared. So later, you don't need to multiply these together now, okay? Whenever you see a complex number multiplied by itself, you can just simply write down as the real part squared plus the imaginary part squared. So what you need to focus is the bottom, is the top here, right? It's the multiplication of these two. So multiplication of these two, 5 by 9, 45. With that, yeah. Huh? Okay. Yeah. So then 9 by this minus J18. This by this, J40. This by that, J squared, negative, positive, so negative 16. Okay, any questions? Okay. Yeah. So then here, bottom here is 25 plus 4 is 29. Top here, 45 minus 16, 29, right? 18 by 18 plus 14 is 58. There. So 29, 58, 29. So you can take out the 29, which is 1 minus 52. Any questions? All good? Yeah. Okay. So let's practice some of this, science here. Okay. Now the question back. Let's go back here. Okay. Actual signs of Z2 to represent this magnitude. So let's give it a proper name here. Give it a proper name. The proper name of that is called margin. And there's an associated concept called argument. Okay, so let me use this complex plane to illustrate this idea. So margin was basically its absolute value z. And argument, notice the word argument is here representing the so-called position here, r, z. It's the angle. It's this angle here. Okay, this angle theta. Okay, that's the argument. So when you learn AC circuits, right, one of the analysis approach for AC circuits, and you haven't learned it probably, is using a so-called phasor, right? Phasor. So the phasor is basically here. This this theta here, essentially is the phasor. So sometimes this is also written as this. So angle Z, okay. So-called a phasor. So the theta, the range of theta, as you can see now, always remember, when you have an angle theta, is always starting from this horizontal axis, right, and then going counterclockwise with positive theta. So the theta will be from here to here, it will be pi, right? And from here to here, it will be negative pi. So the range of the theta is negative pi theta. Right, yeah, like this. Okay. Yeah. Good. So this is also called phase. Let's call it phase here. So in AC circuit analysis, you have this phasor analysis here. Okay, so then let's see if I have that here. How do you calculate theta? right? The theta value you calculate is based on the A and B values here, right? A and B here. So now, look at this triangle here. So tan theta equal to this B over A. So that means theta equal to the arctan B over A. Right? Arctan B over A. Okay, is that good? Yeah. Okay. Now, there's one little thing you need to be careful a little bit here. Let's take an example. That equals to 3 plus, let's see, no, let's see, 3 minus 2, 4. Okay? And the other one is Z2 equal to negative 3 plus J4. So I have two complex numbers here. Okay? Two complex numbers. Okay, can we calculate the actual value of these two? So that's pretty good. We did well. Huh? 5, right? How about this angle? The argument of these two. You don't have to give me a specific value. Just use the formula to tell me what would that be. And inverse B. What's the B value? 4 over 4 over negative 3. So what do I get? I can see the 1 to the 2 equal. Yeah? Why does it make sense? So if you see that it makes sense, then my argument is, can you draw Z1, Z2 on the complex plane? Right, where's Z1? So real is 3, imaginary negative 4. So this is Z1 here, right? This is Z1 here. And what's the definition of theta? Theta is the definition from this horizontal axis to here, right? To here. So this is theta 1 here, right? This is theta 1 here. And where is Z2? Well, Z2 is negative real, positive imaginary. So negative real, positive imaginary. So Z2 is over here. And what's the theta? This is theta, well, I call it theta 1, yeah. What's the theta 2? Theta 2 is from here to here. This theta 2 here, right? This theta 2 here. So now you look at this one here. Now you tell me, does it make sense? Is theta 1 the same as theta 2? No, right? No. Yeah, it still makes sense. So it doesn't. If it doesn't, then what's wrong with here? I don't think there's anything wrong with this formula here, right? I don't think there's anything wrong with the formula. Then what's wrong then? What should you be careful when you use this formula here?
Theta closest to the axis.
Theta closest to the axis.
Like if you use the rest of the 180 from theta 2.
Come again, sorry? What did you say? Yeah.
Like from the imaginary axis. Like anywhere like a 1.
Quadrant, that's keywords here. So you need to be careful where this complex number is, right? Where this complex number. As a matter of fact, maybe you can take all these, just calculate the so it doesn't give you, this guy here doesn't give you a positive angle. Does that make sense, right? So basically, when you calculate theta 2 here, so it looks like this guy is good, right? This guy is good. When you calculate. Okay, this guy's good. But not this guy. Okay, calculator doesn't give you a right result for this guy. So What would you do to the calculator results when you calculate this one here? Plus 180, right? Plus 180. So this one should plus 180 here. Okay. So then, in other words, then how should I know? Basically, how should I know when should I just keep it when it's a calculator, or how should I know it's just a plus 180? What do? You look at the quadrant where it is. Okay, you look at it basically. So draw it out and look at the actual location of the complex number, and then you will know whether it's a positive angle or negative angle. That make sense? Yeah, so I'll just try it. Positive theta or negative theta. The bottom line is, in other words, don't touch the calculator. Right? Yeah. Calculator gives you results, but not necessarily the results you're looking for. Okay. Any questions? Okay. Okay, so I'm going to stop here, and we have some more left on complex numbers.
What I meant was that angle is equal to that one, right?
You mean which one? You mean this one equal to this one?
Yeah, like that.
Yeah, for this case,
right.
Yes.
Like that's what I meant. It's like you go from this angle up to it, the smaller theta.
Okay. Yeah. Yes. In this case, this angle here is basically theta 1 here.
Yeah. It's because in my mechanics class, you always just went from the x-axis up to the.
Yeah.
So does it work if I think of it that way?
Yeah, you that's right. You still need to think of the positive angles from here to here.
Mm-hmm.
Yeah. So positive angle is always
counterclockwise.
Counterclockwise always positive. That's right.
And then positive is negative, or positive is
clockwise. That's right.
So you go this way, but that's what you do is go from there to there.
But
right?
negative doesn't mean you're starting from here. Your starting point is always this 0 here.
Okay.
Yeah. That's all your starting point. Okay. So then you look at where the bar is, going from the zero to there. Is it going clockwise or counterclockwise, right?
And then counterclockwise.
Yeah,
so it's positive.
That's right.
And this is the negative.
That's right. Right. So when you give a negative number to calculator, you get a negative here, right? That's good for this one here, but not for this. So then you need to multiply pi to the calculator results here. I think it makes sense. Yeah.